Student, welcome to my lecture 7. So today I said I'm going to talk about plasma oscillation. In previous lecture I also talked about that d by length and number of particle inside d by sphere. Now the situation comes how you define the plasma oscillation. Basically it leads to the plasma frequency that we denote omega p, and question I'm going to ask myself, what would happen if electron were displaced from their equilibrium position? If you displace something or if you disturb something in equilibrium position, what it react and how it looks like. So I'm going to give you answer for that question and try to understand the plasma oscillation also. If you look here, the electrostatic force due to the ions would pull them back, but the electron would overshoot and oscillation would cause, which is known as a plasma oscillation. And this is very fast kind of oscillation, is so fast that the massive ions do not have time to respond basically. So how we can understand? We have a situation kind. We consider an infinite plasma. We will ignore thermal motions. We will treat the massive ions as not moving. So this you can have a kind of neutral plasma having length L and area is capital A. So if you have excess ions like positive ions, you have a negative ion other side. So this we can say excess electron and excess ions having thickness is x, that is after slab has been moved at a distance x, then suppose a slab of electron is displaced very small distance x, the slab has thickness I said capital L and also considered area is capital A. So you may write equation of motion for the slab, and that is a simple F is equal to ma. So F is nothing but the force due to the motion of electron, and m mass, d is second derivative of acceleration, that's a d square x by dt square. So now the mass of electron in slab is nothing but the me, ne and la. So how many numbers of particle in length slab and area A, which having idea about the mass of electrons in slab. So how the force comes in the electrons, that we are going to try to understand. So we have two oppositely charged sheet, as I said, the positive and negative, other side is negative. The electric field is in between them. So electric field nothing but the sigma s divided by the epsilon 0. As you see in my previous lecture, that is a simple surface charge density, and surface charge density nothing but the charge per area. So therefore the surface charge is E and that is x A divided by area. So A cancel out. So the restoring force which is equal to the charge of electron. So you will have a force, and due the force is equivalent to the charge of electron in a slab and multiplied by the electric field. So your force on electron is minus, because I am talking about electrons, so minus ne LAE, and whatever you will have that ENEX divided by epsilon 0, that is the electric field. When you put here that what A cancel out, so ENEX divided by epsilon 0. So that is the electric field, and simple, that is a simple that which I already talked here in my previous, the mass of you can say this is charge of electrons, right? So equation of motion becomes, you put everything here, mass I have put it here, and again d square x dt square, and this simple all this force expression is here right hand side, this the same cheese you can cancel each other. So finally you will have d square x by dt square, and you will get n e square divided by epsilon naught m e and bracket x. If I assume that this expression without minus sign is my omega p, and that is nothing but the plasma frequency. So our this expression, if you see here, d square x dt square plus omega square x is equal to 0, second order differential equation, well known equation, and which having solution is x a cos omega p t. So will you have this expression, that is a natural frequency. If you calculate, you can calculate natural frequency for the plasma. So FFP 8.98. If you put the electron charge, epsilon 0, mass of everything, so you will get 8.98 square root Ne in hertz, where N in meter per cube, and you will have two relation, one is omega p, another in terms of natural frequency FFP. So for your homework, you look out, can you prove that omega p, what we know that this relation, and lambda d we already know the d by length. Can you get the right hand side the square root of kt by me? You can check and tell me. This is also one expression where both terms lambda d and omega p comes in together. Another, moving ahead, so what are the criteria to have a plasma? So I have written three things, very important. Suppose I am going to ask question, what are the criteria for plasma? So you will have answer. If the dimension L of a system are much larger than lambda d, then whenever local concentration of charge arise or external potential are introduced into the system, these are shielded out in a distance short compared with the capital L, and leaving the bulk of the plasma free of large electric potential or fields. Therefore, outside of the sheet on the wall, so del square phi becomes very negligible or small. Therefore, Ni becomes Ne and give rise to the quasi neutrality concept. Another concept is a criteria for an ionized gas to be a plasma is that it should be dense enough that lambda d is much smaller than L. So lambda d much smaller than L, which give you the collective behavior, and basically it require, in I said previously, that number of particles should be large enough, not a single one, it should be greater than one. If nothing, if single one, no collision occur. If greater than one, there will be a collision inside. So Nd must be large enough to unity or one. And third is very important. If omega p is the frequency of a typical plasma oscillation and tau is the mean free time between collision with neutral atom, so you require one more conditions, that omega p and the mean free time or mean time tau, it should be larger than. So three things always remember to have a plasma for any cases. Thank you. And I have attached one exercise. You will find all numericals. You try to understand these numerical and try to solve the numericals. Thank you. Thank you.